that we did. And we will see, essentially we'll actually do the calculation of the new var versus the old var, and then we'll do the linear approximation and see how we will close the results. Because this is at the heart of risk management. This is really identifying your risk and trying to close it or manage it. So, worked example. By the way, have you seen this? This is in E-class. Do you have a chance to see it? Okay. So, worked example. We have two securities making up a portfolio. Security A, it has a market value of 10 million. It has, say there are annualized volatilities, they could be anything, of 20%, which means that in euros, the volatility of the first security is 2 million. And remember, whenever we talk about parametric VAR, the distinction between log normal and normal is lost. We use interchangeably, we switch from percent to million. Security B. Market value, 90 million. Standard deviation for B is 10%. And this is, it means that the volatility expressed in euros is 9 million. Now what do? I take a portfolio of P. My portfolio P is simply my security A plus my security B. It's just I combine those two securities. So my portfolio of P, what kind of standard deviation would it have? Oh, and one thing, the correlation coefficient between those two securities is 0.5. Now, you remember the formula for finding the variance and as a result the standard deviation of the sum. Who remembers that? Yeah?
The standard deviation of A in A squared plus standard deviation of B squared plus 2 standard deviation of A plus
multiply
times standard deviation of B times correlation coefficient.
Exactly. So in this case, this number is, and this is sigma squared. That's the variance. So the standard deviation is the square root, and let's put the numbers here. 9 squared plus 2 squared plus 2 times 0.5 times 2 times 9. How much is this? Just do it from the calculator.
10.149.
Equals 10.149. What is this? Percent? Million?
Million.
Exactly. 10.149 million. So we just found sigma of this portfolio. Now, if I want to find the marginal sigma or marginal var, okay, so if I want to find, say, the var of this, it would have been at 99.9, at 99% 1 year, I would just multiply this by 2.33. Okay. Suppose now I want to find the marginal. And how do I find the marginal var? I want to increase this security here by 1. So the 10 million will become 11 million. 20%, that's property of the security. This doesn't change the quantity. However, the 2 million, which is the actual dollar amount, euro amount of the volatility, is going to go to 2.2 million. Everything else is the same. By the way, does this correlation coefficient change if I change quantities? No. Would the beta have changed if I change quantities? Remember, the beta has a correlation coefficient with the portfolio. Yeah, what's the difference between this correlation coefficient and the correlation coefficient with the beta? This is the correlation coefficient between one thing and the other. The beta is the correlation coefficient between this and the portfolio, which includes this. You would see the analytical approach. But this thing is given. Rho AB is 0.5, so it doesn't change. So my new sigma is 9. This becomes 2.2 squared. And this becomes 2 times 0.5 times 2.2 times 9. And instead of 10.149, how much is it?
10.278.
10.278. So, this difference, what does it tell us? It tells us, in words, that a 1 million incremental position in asset A will result into the difference of this is 129,000 of incremental standard deviation. Okay? It's the same thing that's in there. So this is clear enough. Okay? This is brute force. Just go ahead and do it. Let's go to the next one. The next one will apply the linear approximation that we calculated in the previous lecture. Okay? And what did this say? It says that the partial derivative of sigma with respect to the weight of asset A is the covariance between asset A and the portfolio over the variance, the standard deviation of the portfolio. This is what we proved last time. Now, one thing which may or may not have struck you here, okay? We used to talk about weights as fractional contributions to the portfolio. Okay? Has anybody wondered, when I say this derivative with respect to weight A, does it mean that all other weights have to be adjusted so that the summation is still 1? No, it doesn't. And this is what we're going to show here. If we're very, very strict about this, we shouldn't call them W's any longer, because they don't sum up to 1. Because I just left everything else unchanged and then changed one of them. Just as the value of the portfolio here no longer sums up to 100. It sums up to 101. This is an aside that we should keep in mind. So this is kind of a loose notation. But loose or not, this is the standard way of dealing with this in the industry. So in this case, what do we have? In this case, if you remember the Taylor expansion. Okay? Taylor expansion, what did it say? It says that Taylor expansion which is the linear approximation. It says that delta F is df dx delta x. This is the linear approximation. Okay? We apply exactly the same thing here. Okay, we say delta sigma or delta omega A is covariance RA RP sigma B. Everything still here. Everything still here is in percent. Okay? Let's just try, because in the end, we're interested in euros. Okay? And very, very important, once we move out of this kind of portfolio construction and go into derivatives, percent makes no sense anymore. We'll have to speak in euros. So, this sigma of d omega A is this. Just applying the Taylor expansion, we say delta sigma is simply A times sigma times delta omega A. Again, what we want is we want euros. So, we say the following: delta sigma times the value of the portfolio, P, is going to be sigma delta omega I P. Sorry, omega A P. Okay? But what is this?
Euro.
This is what we're trying to find out what it is. These things we'll talk about in a moment. And this thing, delta omega A times the value of the portfolio, is the plus 1 million we saw in the previous example. Okay? So we're still not there yet, but we are going. The one problem that's still present is this. What is beta A? Beta A is the covariance of asset A with the entire portfolio. What was given and what is generally given in when I start doing the portfolio construction, it's rho AB. It's the correlation of the one asset with the complement of the portfolio. So we have this information to go by if we want to calculate the beta A. Let's do that. It's a good example of going back to the basic definitions to try to calculate something which is not given immediately. It's not immediately apparent. Now, covariance. What is the definition of the covariance of two things? You remember the definition of the covariance of two things? Definition of the covariance of two things is the following. Covariance between the RA and RB is this. The expected value of RA times RB minus the product of the respective expected values. So RA, RB. This is the definition of covariance. In our case, let me correct this. We don't want RA, RB. We want covariance. And this, by the way, is given. This was given in our problem because we had rho AB, we had sigma A, we had sigma B. This is, by definition, we have this, we have that, we have that, so we have that. But what we are really after is not covariance rho A or rho B, it's covariance RA, RP, the portfolio. However, P, you remember our very first lesson of looking at portfolio returns. Our portfolio P, what is it? It's 90% A, I'm sorry, 90% B and 10% A. So, just as we had proven in the first class, the return of the portfolio, the rate of return of the portfolio is going to be 10% the rate of return of asset A plus 90% the rate of return of asset B. So this is really the covariance. Are we running out of markers? This is really the covariance of RA and let's just go in by brute force and apply definitions. So this is the expected value of omega A RA plus omega B RB minus the expected value of A, times the expected value of RB. Expected value of RA times the expected value of omega A RA plus omega B RB. But you remember, the expected value of the sum of things is the sum of the expected values. The expected value of the product of something with a number is the number times the expected value of something. The expected value of a product is not the product of the expected values. Why? Because their difference is the covariance. But by just taking the expected value operators and rearranging things, what do we get? This is, I'm just taking a number out. Okay? Again, I'm taking a number out of here, and I'm breaking an expected value of a sum. Okay? This is, here I can just break the expected value here and take expected value, omega A, take it out, and this is the square of the expected values. Instead of the expected value of the square, minus omega B. Let's start combining terms. I did this color-coded here. Does this for-sum term look familiar? Essentially, if I take this and this, what is this? Sigma square A. It's the variance of A. So this is omega A variance of A. And if I take this and this, what is it? Covariance. But this was given. You remember that? Omega A is what? Omega A is 10%. Sigma square of A equals, what was 20% squared, if I'm...
Yes.
Okay, plus 90%. Rho AB 0.5 times 10% times 20%. So I got the numbers from the problem. So this is the way to go from the correlation of two things with each other to the correlation of each of those things with a superset. And this is 0.013. Okay, just going through the numbers. This is the covariance. The coefficient that we said, it was covariance over sigma p, which was 0.03 over this number here, which is 0.128.
So we need the sigma p also.
We need the sigma p, yes. Because that was the formula. It wasn't just the covariance. It's the sigma p. Either you have it as covariance over sigma or as beta times sigma. Okay. So, This coefficient now relates what? Dollars with dollars. I don't have it in here. It's dollars with dollars. $1 million would give me 0.128 millions of additional signals, which is the 129K. It's not exactly the same, but it's close enough for a linear approximation. Because this is not a small change. This is... Yes, yes. Ευχαριστώ πολύ. Μπορείτε να βρείτε και ένα πιο αναδόντους.
Εγώ, με τίποτα.
Okay. So this is it. Pure brute force calculation and the linear analytical approach, parametric VAR approach, can give the same result. I think this should give you a little more comfort. Because this is down the line of what you asked. There was there wasn't a clear distinction between percent, dollars, amounts, fractional sigmas. I think this clears it. Okay. So, we charge ahead. Okay, we are starting now to go into real risk management. Let's recap from where we left. In the previous lecture, we saw this whole formalism of incremental VAR, marginal VAR, component VAR, applied to sets of cash securities, which each of them had a volatility which is proportional to a measure of uncertainty and the cash amount, the value of that position. Okay? This whole approach breaks down the moment you start discussing derivatives. Because a derivative is an entity which may have zero value originally, but it could have tremendous impact on the risk of the counterparties entering the derivative. That's why it's a pretty dangerous beast. You don't really have to have money. I mean, in the old days of the stock market, you had to have money in order to be able to lose money. You had to have money that you go and buy the stock. The stock wouldn't go well, you would lose money. With the derivatives, you don't need to have money in order to lose money. Which means that you can very easily lose money that you don't have. What happens when you lose money that you don't have? We saw this in 2008 with AIG. AIG, the first big intervention of the American government was to extend credits to AIG to pay for collateral calls against Goldman Sachs. And at the time, Paulson had just come off Goldman Sachs, so there was a big discussion about whether he was using public money to essentially bail out not AIG, but his own employer. So, we need a new framework to capture the risk of derivatives. Suppose, let's not move directly into derivatives, let's move into a different kind of beast, which still has a cash value, the bond. Okay? We need some measure to connect the riskiness of the bond to the riskiness of the true underlying risk factor of bond markets, which is the interest rate. Now, I understand that most of you have seen this measure before. It's called the duration. Okay? So, if we have a duration, if we have a change in interest rates.
Sorry, could you repeat the duration? What explained?
The duration. Let us go. The duration. The duration is simply this. It's 1 over P times dP over dr.
No, what explained in risk management? No, in the bond, I know in the bond. What
do you mean
explained?
in risk management?
Now we explain the duration in bond
Yes.
only. Okay.
It's duration in the bond.
I'm okay.
So it's
With
still a
this.
cash instrument. It's still a cash instrument.
Hmm?
But instead of in the stock whereby there was a one-on-one correspondence, 10% drop in the stock price, 10% drop in the stock price. The duration is different because we need to translate a 50 basis point change in interest rates. We need to translate this to a change in the value of a bond. And essentially, that's the big formula. Okay? The fractional change in the value of the bond for a given change in interest rates, it's called the duration. This is a matter of definition. Now the question is, why is it called duration? And it's called duration because it has units of time. And why does it have units of time? Because this is units of price, this is units of price. And the rate is generally percent per unit of time. So 1 over per unit of time is units of time. So it's called duration. That's one reason. The other reason is for reasonable physical maturities and low interest rates, the way interest rates are now, and certainly for anything we're going to do in this class, duration is pretty much equal to the physical maturity. Now, don't ever quote me on that to anybody out of here. This is not exact, but since this is not a class in bond pricing, this is going to be good enough for the underlying principles of all this that we're going to discuss here. So, as an example, suppose we have a 7-year bond. It has a notional amount of 100 million. It has a price of 110. And interest rates go up from, say, 2%. They go to 3%. Sorry, there's a minus. It's the inverse price yield relationship. So, can one tell me what's going to be the price impact in this position of 110 million?
It decreased.
It will decrease by how much?
I don't know.
Let's start. What do we need to know to see how much it will decrease? We need to know the duration of the bond. But I said that this is a 7-year. 7 year of remaining maturity.
We use this approximation.
Exactly.
Okay.
We use this approximation. So our drop in price is going to be minus 7 times 100 million times 110 over 100, because we said that the bond has a price of 110, times 3% minus 2%. Okay, so this is about how much roughly? 7.7 million.
Can you explain the formula again?
Yeah. You accept this as a matter of definition. Okay? We can also have a short proof. It's also in Excel. But essentially it says that the fractional change in the price of a bond for a given change in interest rate is minus the duration. Which means if I do that, if I extend that, it will be the following. It means that P equals P times minus P times duration times this is exactly what we said here. Minus, here it is, the price of the bond, the value of the bond is this thing here. Okay? And the DR is this thing here.
So this is a 7.7 million decrease.
It's a 7.7 million decrease. So 100 basis point or a 1% increase in interest rate will give me a 7.7 million decrease in the value of this bond.
Can I ask something else?
Yes, please.
In which case will the duration not be equal to the physical maturity?
Generally, it's not equal, it's approximately. When you have bonds that have a high yield,
Early.
a high yield, then the duration is smaller. Because think about it as if I have bonds with high coupons, the center of gravity of the payments moves earlier. If I have bonds that are very, very long term, if I have bonds, if I have a bond which is a perpetuity,
Exactly.
duration is not infinite. Duration has a limiting value of 1 over yield for perpetuities. So if I have a bond, because first of all, if I have a bond in perpetuity with 0% interest, it's a non-entity. It's a non-instrument. That's a non-instrument. If I have a bond which comes out at par in perpetuity and has a coupon of 5%, there are some such bonds. They exist. Then this means that in perpetuity, I will be paying 5% and never have to give capital back. Now, obviously, if interest rates go up, this will have a lower value. If interest rates go down, this will have a higher value. Locally, for local changes, the duration, instead of being infinite, it has a limiting value of 1 over 5%. So it has a limiting value of 20. Okay? Locally,